Hello, we have a new exercise here about the relative motion. So we will deal with absolute motion, relative motion, the driving motion. So let's start with this exercise. A particle m released without initial speed from a height h falls by performing an uniformly rectilinear motion of acceleration g along the vertical axis O1 y1. So we have a particle m released, it was at rest, so it had a v0 equals 0 from a height h. So here we draw the frame O1 x1 y1, where at t equals 0 m was at x1 equals 0 and y1 equal h at a height h. It has a uniformly accelerated rectilinear motion of acceleration g. So it's a free fall. This is a free fall motion. So the acceleration is equal to a constant, g or minus g. Here it's equal to minus g along the vertical axis O1 y1. So they called this frame O1 x1 y1. Okay, O1 is the origin of O1 x1 y1. It's it's associated to an observer at rest. So we can consider that O1 can be an observer at rest that is not moving. So this is the stationary frame. Question A. Determine the position vector of this particle with respect to a car that is moving at constant speed v equal v along I1 along the axis O1 x1. We recall R absolute equal R driving plus R relative. So we know that an observer at O1 will see the object M moving downward vertically. But for an observer in a car that is moving to the right, the object M will appear differently. The object M will have a position vector different than the position vector observed by O1. So, in fact, this is to say that OM is different than O1. And in question A, they want us to find the position vector of M with respect to a car that is moving. So they want us to find OM, the position vector with respect to the observer O. So we need to find, in fact, OM. They remembered us with this expression, okay, but we already know it. So the position vector, the absolute position vector is equal to the driving position vector plus the relative position vector. So we need to find OM. So let's start, in fact, to distinguish between the two frames of reference. The first frame of reference, O1 x1 y1, that is not moving. The observer O1 is at rest. And the second reference frame, which is related to the car, the moving car. So here, OXY is moving to the right with a constant velocity vector. Okay, we can also distinguish two different systems of unit vectors. So here we have I and we have J. Okay, so this is for the moving frame, and we have in the absolute frame we have I1 and J1. What is the relationship between O1M and OM? In fact, we know that RA equal RB plus RA with respect to B. This means that the absolute position vector is equal to the driving position vector plus the relative position vector. If we apply this formula to our exercise, we need, in fact, we are finding the position of point M. So our system is point M. So we are finding the absolute position vector for point M. So here we can consider, so the absolute motion, the absolute position vector for point M is equal to RD is related to the position vector of the moving frame, okay? D refers to driving motion, and the driving motion is in fact related to the moving frame, and our moving frame is the car, so we can precise that RD is for the car plus R relative. So we are considering the motion of point M relative to our driving car, to our driving system, which is the car. So R relative is the position vector of M relative to the car. Okay, so this is to say that RA is for M, RB is for car, and RA with respect to B is M with respect to the car. In fact, they want us to find the position vector of M with respect to the car, so they want us to find RR. Okay, this is another way to say that O1M is equal to O10 plus OM. Why? Because RA, the position vector of point M, A refers to absolute. So here the absolute motion is observed with respect to O1. So RA is observed by O1. So the origin is O1, and you are studying M. So O1M is equal to RD, so this is the position vector of the car. The position vector of the car is O10 plus R relative is for the position vector of M with respect to the car, so the position vector of M with respect to O. This is OM. And this is mathematically correct because O1M equal O10 plus OM. Oh, so we need to find R, we need to find this term. So R, position vector of M relative to the car, so R relative is equal to R absolute minus R driving. Okay, we need to find now RA and RD. What is RA? It's the position vector of point M as observed by O1. Okay, O1 observes that M is making a free fall with a constant acceleration equal to minus g. So M is making a uniformly rectilinear motion, a uniformly accelerated rectilinear motion. We have a constant acceleration, so we can guess the position vector. It's equal to here R of point M as observed by O1 is just Y1, so it's along J1. It's along J1, and we know that Y is equal to half AYT squared plus V0 T plus Y0, and then we can replace AY with minus G. So this term is only for RA. Now we need to find RD. We need to find RD, so it's the position vector of the car. Sure, it's as observed by O1. The position vector of the car as observed by O1, it's equal to what? In fact, we need to understand the motion of the car. It's a uniform rectilinear motion, so we can say that R is only along X, so it's along I1, and it's equal to VT. So RD is along I1 and RA is along J1. So we found the position vector. We still need to replace AY with minus G, V0 with 0 because M was initially at rest, and Y0 should be replaced with H. Note here also that J1 is equal to J and I1 is equal to I. Now question D, deduce its trajectory, its relative trajectory. its relative trajectory. So based on the relative position vector, we need to find the relative trajectory. It means that we need to find the relationship between y and x, and an equation independent of time for this relative motion. So we have, in fact, the first term is the y, and the second term is for x. So to find the relative trajectory, we need to rewrite the relative position vector of m with respect to the car. So we can write that x is equal to minus vt and y is equal to minus half gt squared plus v0t plus y0. Okay, here v0 is 0 and y0 is h. So we need to get rid of this t. Okay, we can find the expression of t from the first expression as a function of x. So t is equal to minus x over v, and let's replace t, the expression of y, and we will obtain y equal minus half g parenthesis minus x over v parenthesis squared plus h, and thus we obtain simply the expression of y as a function of x independently of time. We can notice that this is the equation of a parabola. So the trajectory of m in the system linked to the car OXY is a parabola. This means that the car will see m making a parabola, whereas the observer O1 will see m just falling down. So I will repeat, O1 will see m just falling down vertically, whereas O will see m making a parabola like this. And this is the main difference between the relative motion and the absolute motion, because in fact O1 will see the absolute motion because O1 is at rest, whereas O will see different thing. O will see that m is making a free fall plus a motion along x. O will see the trajectory of m as a parabola.